Good morning, students. In our previous classes, we have completed a nuclei chapter. First part of the chapter nuclei completed, and second part radioactivity concept also completed. And yesterday we discussed nuclear reaction, what is alpha decay, what is a beta decay, and what are the equations and examples we have given in the previous class. So the total theory part of the chapter completed, and in this class we will start numericals, textbook exercise numericals will start. If you have the textbook, open the textbook nuclei chapter, and we'll go for solutions according to that. And before that, few formulae I'll give, note down that formula also. And in radioactivity, after learning all the concept of radioactivity, so what are the uses of the radioisotopes? Generally in laboratories, by using simple techniques like by bombardment of the particles with some unstable nuclei or maybe stable nuclei, we can convert one nucleus into other nucleus. That process generally called as artificial transmutation. Generally, most of the elements are naturally available, like uranium, plutonium, thorium, or iodine. Such type of some elements are available, but that is called natural radioactivity. Means the spontaneous emission of the radiation by naturally available radioactive elements are called natural radioactivity. But artificially also we can produce. So that is given by Rutherford. So artificial radioactivity concept. How it is possible means in the laboratory, a suitable element we have to choose. It is made to bombard with a particle like a proton, neutron, or maybe alpha particle, so that one nucleus will be converted into other nucleus. That transmutation, that process called as artificial transmutation or artificial radioactivity. So by using this technique, we can produce radioisotopes also. But after getting the radioisotopes, they are having a lot of uses, various fields. They are having number of uses. For example, in the medical field, if you are using radioiodine, that is also isotope of the radioiodine only isotope, and purpose of the radioiodine to monitor or to estimate the problems in thyroid glands. If a person is suffering any thyroid problem, by using a radioisotope, we can examine and we can monitor and we can cure the thyroid problems. Radioiodine. For example, if any person is suffering with a cancer, they can use radiocobalt. By using a radiocobalt, we can cure the cancer. In the treatment of the cancer, we can use radiocobalt also. That is also one of the use. And radiophosphorus is also the radiophosphorus, radiosodium. So for example, radiosodium, if you are using, so we can cure anemia problems. And also any blood circulatory problems are there, also we can monitor where the blood clots are there. And that clot, if you want to remove, we can inject a small quantity of the radioisotope, and throughout the body that will circulate, and any restrictions in the blood is there, that will cure. And also radiophosphorus we can use for skin diseases also. Any skin diseases are there, we can cure the skin diseases by using a radiophosphorus also. So there are a lot of uses in a medical field. In the same way, in industrial, for example, any huge metal sheets or metal tubes are there, any holes or any flaws or any cracks are there. So by using a radioisotope, we can examine or we can find the defects in the huge iron sheets, or maybe iron tubes, or maybe in case of the iron girders, we can identify cracks also. And moreover, in case of the automobile industries, we can select a proper lubricant for the given vehicle, like 2T oils or 4T oils you are using. The oil is having whatever lubricant you are using, that is having a more thick or thin or more viscous or less viscous. So that can also be monitored by using radioisotopes only. And also in case of archaeological field, for example, any fossil, like archaeology persons, they collected any fossil from the earth, and that fossil how much age ago it lived, if you want to identify like dinosaurs or something, or any species if you collected, and we can estimate the age by using carbon 14 isotope, that is called carbon dating. Same way, if you want to find age of a rock, or age of the mountains, or age of the earth, if you want to find, we can use uranium 238 mass number, so that is called uranium dating. And also by using a radiophosphorus in the agriculture field, when we are giving a small quantity of the radiophosphorus to the plant, and we can monitor the growth of the plant. Whenever we are giving a fertilizers like our pesticide or fertilizer we are given to the plant, and we can monitor how the plant is absorbing the fertilizer, and growth increasing or decreasing, or we can monitor also. And in this way various fields we can use the radioisotopes. Sometimes in case of human body, any brain tumors are there or any tumors are there, so we can inject a small quantity of the radioisotope. The radioisotope can move throughout the body and it can identify where exactly the tumor is there, and location we can identify, diagnosis, and then they will cure the tumor also. That is also radioisotopes only. And also whenever we have taken a small quantity of the medicine, for example at the time of the research, whether the newly found tablets or maybe medicine or vaccine, how they are working on a particular person, means if you inject a small quantity of the radioisotope like in the order of the micrograms or milligrams, very small quantity, and that will move throughout the body, and that can give the information how the medicine or vaccine whatever we have given to the patient, how it will be circulating throughout the body. So also will be monitored by using the radioisotopes only. So there are a lot of uses in almost all the fields: medical, industrial, geological, agricultural, and also archaeological. In all the fields there are the uses of the radioisotopes. That is the radioisotopes concept only. Now we will give some important formulae, and in textbook they given some data also. Instead of giving for each and every problem, they are starting only at the beginning, they given data like what is the mass of the neutron, what is the mass of hydrogen, and what is the Avogadro number, what is the 1 AMU value, all these values also they given, and a few formulae I will give. Note down this formulae. For nuclei, important formulae, all the formulae not necessary, already in a regular discussion I have given some important formulae, right? So in this chapter starting we discussed about isotopes, isobars, isotones, that concept, composition of the nuclei. In that composition of the nuclei, isotopes I have given one important concept, how to find average atomic mass. Average atomic mass we can find, that I will write M average is equal to M1 x1 plus M2 x2 divided by x1 plus x2. Here your choice, M1 or A1, any letter may write, or W1 may write, average atomic mass or average atomic weight, average atomic mass. So mass of the first isotope and its abundance percentage plus mass of the second isotope, average atomic mass of the second isotope into its percentage divided by total percentage. Always x1 plus x2 must be 100, should write. So in this M1 M2 given, x1 x2 given, we can find average atomic mass, correct, based on the question. If 3 isotopes are given, plus M3 x3 by x1 plus x2 plus x3. Next one more, what is the charge means? So charge of the nucleus is equal to formula plus Z into E, should write, charge of the nucleus formula. And one more, mass of the nucleus, Z into MP plus A minus Z into Mn, or we can write mass of the atom, Z into Mh, should write, plus A minus Z into Mn. So understand here and here difference, it is only nuclear mass, protons and neutrons, but here it is atomic mass means protons plus neutrons plus electrons. Generally mass of the proton plus mass of electron both combined equal to hydrogen atom, that's why Z into Mh should write. Next one more, nuclear density rho is equal to mass of the nucleus by volume of the nucleus, mass of the nucleus by volume of the nucleus, that is equal to 3 into m by 4 pi into r naught cube. M means mass of the nucleon, maybe proton or neutron. R naught is equal to constant, proportionality constant 1.2 Fermi or 1.2 into 10 power minus 15 meter. Then the delta M mass defect ZMP plus A minus Z into Mn minus mass of the nucleus, or Z into MH plus A minus Z into Mn minus atomic mass. Both same or capital M, right? It is in terms of hydrogen. It is in terms of protons. Nucleus, wherever nuclear mass given, take this one. Directly atomic mass given, use this formula. Next, binding energy formula. Be is equal to delta M into C square joule, or delta M into 931.5 MeV. Specific binding energy is equal to Be by A, that is equal to delta M into C square by A joule, or delta M into 931.5 by A MeV, mega electron volt. So binding energy, specific binding energy, and this concept. And one more general formula, E is equal to mc square, or M is equal to E by C square. Einstein mass energy equation. After Einstein mass energy equation and this concept, we have given nuclear fission and also nuclear reactor. That concept I have given. In a nuclear reactor, how to find the power? Here, or we can write total energy released or produced. Total energy produced by a nuclear reactor. I'll write E dash is equal to N into E. E dash is equal to N into E. E means energy released per fission. For one fission, how much amount of energy emitted, or for one atom, how much amount of energy emitted. For all the N atoms, what is the total amount of energy? That's the formula. Here N means the number of atoms, E is equal to energy per atom for one nucleon. Or what is the power? How to find the power means P is equal to E dash by T, the rate of doing the work, generally power, but here total amount of energy released by the reactor divided by total time taken. But E dash place we can also write N into E by T we can write. From this, if you want to find how many fissions or how many atoms participated in the reaction, N is equal to PT by E we can write. Take all the values left side, N is equal to PT by number of atoms participated. If you want to get this much power in a nuclear reactor, how many atoms should be participated? If these many atoms participated, what is the mass of all the atoms? So this type of questions will be asked sometimes. But whenever if you want to find the number of atoms when mass given, use Avogadro hypothesis concept. Generally, according to Avogadro hypothesis, number of atoms N is equal to Avogadro number into mass of the sample by mass number. It is a formula. Number of atoms is equal to Avogadro number into mass of the sample by mass number. From this, if you want to find a volume mass, M is equal to number of atoms into Avogadro, number of atoms into mass number by Avogadro number. Na I should write. So in place of the N, we can also substitute this formula here. So based on the given problem, use this one. It is about a nuclear reactor and also nuclear fission process. Here only we can write delta M, one more formula, mass defect. is equal to mass of the reactants minus mass of the reactants minus mass of the products. Mass of the reactants minus mass of the products. Mass of the reactants minus mass of the products. Mass of the reactants minus mass of the products. So it is about nuclear fission. In nuclear fusion also there will be no new formulae, same only. And next we have radioactivity concept is there. And for finding a Q value of the reaction, we will follow normal formula only. Q is equal to delta M into C square, or mass of the reactants minus mass of the products. That formula only we have to follow. And yesterday I have given how to find the Q value of the reaction, the kinetic energy carried by alpha particle, kinetic energy carried by daughter nucleus also yesterday given. So we have to follow that method. Next radioactivity formula we should write N is equal to N naught into e to the power of minus lambda t. In terms of the mass, M is equal to M naught into e power minus lambda into t. In terms of the activities, R is equal to R naught into e to the power of minus lambda t. Number of atoms, mass, and also activity of the sample in terms of activity. So here only to find number of atoms, N is equal to N naught by 2 to the power of N. Number of remaining atoms in the sample, original number of atoms, number of half-lives. Or we can write N naught by 2 to the power of small t by capital T. Capital T half-life, but small t given time should take. Similarly, M is equal to M naught by 2 to the power of N, that is equal to M naught by 2 to the power of small t by capital T. Similar formula, but in terms of masses. Same way, activity formula should write R is equal to R naught by 2 to the power of N, that is equal to R naught by 2 to the power of small t by capital T. Generally here number of half-lives we know formula. Number of half-lives N is equal to small t by capital T. N is equal to small t by capital T should write. Next one, half-life formula, capital T is equal to 0.693 by lambda, or lambda is equal to 0.693 by capital T. Capital T is nothing but half-life of the sample. And tau is equal to 1 by lambda, or lambda is equal to 1 by tau. Half-life, mean life, and both relation also we know. So T is equal to 0.693 into tau, correct? Or tau is equal to 1.44 into T. Half-life, mean life relation. Half-life and mean life relation should write. And activity of the sample we know R is equal to formula lambda into N. R is equal to lambda into N, but a lambda place you can write 0.693 by capital T into N is equal number of atoms equal to Avogadro number into mass of the sample by mass number. So based on this we can find various formulae, various three, four problems we can solve by using this formula. It is important. In textbook also 2 problems given based on this formula. So it is one of the important formula for 5 marks in numericals. If for example in a nuclear radioactivity process, a parallel decay takes place. 2 atoms, one alpha and one beta emitted, for example, then average we should write T is equal to T1 T2 divided by T1 plus T2 you should write. Average half-life of 2 decays. If it is for example a average mean life, tau is equal to tau 1 into tau 2 divided by tau 1 plus tau 2 you should write. So if you want to find directly n formula, from the formula n is equal to n naught into e to the power of minus lambda t. I will write e power minus lambda t is equal to n by n naught. Taking a reciprocal on both sides, e power lambda t is equal to n naught by n. Take e also right side. If we take e right side means it become logarithm. So lambda t is equal to log n naught by n base e. I will convert this value and I will take lambda also right side. Time taken t is equal to 2.303 into log n naught by n base 10 divided by lambda you should write. But lambda place what you can write means here already given 0.693 by t. Lambda place you can substitute here. Therefore t is equal to 2.303 into log n naught by n, log n naught by n base 10 divided by lambda place I am writing a 0.693 by t. So we can take t to numerator, so that 2.303 by 0.693. If you divide 3 point, you will get 323. 3.323 into capital T into log n naught by n base 10. So it is also important formula, remember carefully. So directly if you want to find after how much time the number of atoms becomes 10% or 20% or 30% are given, use this one. Here capital T, half-life, n naught initial number of atoms, n number of atoms after the given time. So same way we can use here, T is equal to 3.323 into capital T into log m naught by m. In the given numerical, masses given, use this formula. Number of atoms given, use this formula. If activity given, then R I should write T is equal to 3.323 into capital T into log R naught by R base 10 in terms of the activities. And in this here, whatever I have substituted, lambda place we can write 1 by lambda is equal to tau, mean life also write from this formula. T is equal to 2.303 into log n naught by n base 10 divided by what is there, lambda. But 1 by lambda is nothing but mean life, tau. So we can also write tau here. Tau. Without a half-life, we can write tau also. 1 by lambda place I am writing a tau, mean life or average life. Or we can write T is equal to 2.303 into tau into log m naught by m in terms of the masses base 10. Or T is equal to 2.303 into tau log R naught by R in terms of activities. These are the important formulae and also some important data also there. Some important data given. In textbook starting they have given the important data, give the textbook. I'll write that data. If you have the textbook, go through this one. NUCLEI chapter, page number 462. If you have the textbook, page number 462. Check the data given, and they mentioned you may find the following data useful for solving the exercise. While solving all the numericals, and we can use this data. And again for each and every problem, they have not mentioned the data. So for all the problems, you have to use this data only. Correct. So what they have given means first E given, charge of electron. So charge of electron E is equal to 1.6 into 10 to the power of minus 19 coulomb. Charge of electron given. And next Avogadro number given, N 6.023 into 10 to the power of 23. 6.023 into 10 to the power 23 per mole. Next 1 by 4 pi epsilon naught. If anywhere required, use this value also. Is equal to 9 into 10 to the power of 9. 9 into 10 to the power 9 Newton meter square per coulomb square. In the first track electrostatics also Coulomb's inverse square we have used this value. Next Boltzmann constant given. Boltzmann constant K 1.381 into 10 to the power of minus 23 joule per Kelvin. That is a Boltzmann constant. 1 MeV, 1 mega electron volt or million electron volt, equal to 1.6 into 10 to the power of minus 13 joule. And 1 U means nothing but atomic mass unit. In terms of energy given, 931.5 MeV per C square. Because from the formula E equal mc square, m is equal to E by c square. M is equal to E by c square. M means 1 atomic mass unit, 1 AMU, equal to E means 931.5 MeV per c square, should write, divided by. Next, 1 year. So 1 year also they given directly. If anywhere required means you can use directly this value. 1 year. Actually 1 year means how to convert into seconds? 365 days. Into 24 hours, into 60 minutes, into 60 minutes. On calculation, all the values will get 3.154 into 10 power 7 seconds. 3.154 into 10 to the power of 7 seconds. So directly we can use this value. Whenever if you want to convert 10 years given, so 10 into this value. 27 years given, 27 into this value directly. And one more, mass of hydrogen. MH is equal to 1.007825 AMU. 1.007825. Mass of the neutron 1.008665 AMU or U. Next, mass of electron ME 0.0000548 AMU. Next, mass of hydrogen 1H1. Mass of helium He 2He4. Mass of helium is equal to 4.002603 AMU U. So it is the total data given. So this data we have to use for calculations. Are the same? Any set? Okay. Now we'll discuss the problems. Okay, I think you have copied this data, and while solving the problems in textbook, we have to go through this one, and for each and every problem, we have to follow this one only. Now, if you have the textbook, open the textbook exercise. Now, first problem. So, total 21 questions given, 21 problems given. Check question number 1. Two stable isotopes of lithium, two stable isotopes of the lithium given, or I'll go through the textbook directly. Okay. So check first problem. Two stable isotopes of lithium, Li, atomic number 3, mass number 7, and one more, atomic number 3 and mass number 6. Two isotopes are given. They are having respective abundances 7.5% and 92.5%. So they are having availability in the nature given. One isotope Li 3,6 available 7.5%, but second isotope having 92.5% available. Then these isotopes are having a masses 6.01512 and also 7.01600 U respectively. Then find the average atomic mass of the lithium. Average atomic mass problem given. Right, first one, textbook exercise. So textbook numericals. So from NUCLEI chapter, it is 13.1. First problem 13.1. Chapter number 13 and numerical 1. So they given first lithium Li 3,6. For lithium Li atomic number 3, mass number 6, they have given mass and also they have given abundance. Abundance means I'll take percentage x1. So mass of the lithium 6.01512, 6.01512 U, unified mass or atomic mass unit, but its availability 7.5%. That is for first isotope lithium. Second one for lithium with a 3, 7. Here also same mass given and also abundance x2 value given. So mass of this isotope 7.01600 unified mass and a percentage value 92.5%. It is the first question. This A. What they are asking? What is the average atomic mass of lithium? M you should calculate. M1 given, X1 given, M2 given, X2 given. What they are asking? Average atomic mass. So already I have given formula. Average atomic mass. M is equal to formula M1 X1 plus M2 X2 divided by X1 plus X2. But always the denominator must be 100%. So M1 X1, M1 is equal to 6.01512 into X1 is equal to 7.5 plus M2 value 7.01600 into 92.5 divided by 7.5 plus 92.5. Here the total denominator must be 100%. Now you should add multiply both the numbers. First one 6.01512 into 7.5. 13.51512. Same way, plus second one 648.98. 7.01600. 7.01600 into 92.5 into 92.5. How much is 648.98? All zeros, sir. All zeros, sir. So total here 1, 2, 3, 4, 5 digits given. Here also you should write zeros. You should write. After decimal point they have given 5 digits. I'll consider all. Now check once again. 6.01512 into 7.5. If you have the calculator, do this one. Calculate. 6.01512 into 7.5. Now use the formula. Average atomic mass is equal to m1x1 plus m2x2 by m1 plus m2 you should take. From the formula, average atomic mass m is equal to m1x1 plus m2x2 divided by x1 plus x2. Now substitute that value. If you substitute, m is equal, already they have given 10.811 is equal, m1 is equal to the given 10.01294 into x plus second value is equal 11.00931 into 100 minus x whole divided by x plus 100 minus x. Here minus x plus x get cancelled. Now we have to simplify. 10.811, here denominator 100 is there, take 100 left side into 100 is equal to right side 10.01294 into x plus this value is equal to 11.00 into 100 is to take, that is equal 1100.93. 1100.93 minus 11.0093 into x. So this value I am multiplying with 100 means 1100.93931 minus 11.00931 into x. Now we have to simplify this value. If you multiply this one, that is equal to 1081.1 equal to this value same 10.01294. Do one thing. Okay, 10.01294. Here these two we should simplify. These two may simplify directly. First I'll write 1100.931. Here subtract this value minus this value. 11.00931 minus 10.01294 minus 0.99637 into x. Take this value left side and this value right side. That equal 0.99637x is equal to 1100.931 minus 1081.1. Subtract, after subtracting how much? 19.831 divided by 0.99637. 19.90. Okay, approximately 19.9% we can write. Right after this one, 19.9%. So abundance of the first isotope of the boron, that is 510, is 19.9% available. Already I have given x1 is equal x%. So for boron 510, what is availability means x1 is equal to x% means 19.9%. What about the second isotope of the boron 511? 511 means you should take x2 is equal to 100 minus x, that equal 100 minus 19.9. That equal 100 minus 20 is 100 minus 20 is equal to 80%. That equal 80.1%. Correct? 80.1% should take. These are the two answers. So boron 510 availability 19.9%, approximately 20%. Whereas second isotope boron 511 nearly 80% available or 80.1% available. That is for both the problems. So formula same, but data and calculation different. So quite a lengthy calculations in this chapter. Formula and the process are not difficult. The calculation part only appears to be lengthy. So because after decimal point nearly they are given around 5 to 6 digits. In some of the problems they have given around 5 to 6 digits are given. Second question I will give, and you may try for next class. 13.2. Second problem 13.2. 3 stable isotopes of neon. One is a 1020, 1021 and a 1022. So first isotope they given neon, atomic number 10, mass number 20, and the second isotope 21, 22 given. They are having average abundances are given. First one 90.51%. Here x1 is equal given 90.51%. And also its a mass given 19.99. Its a mass m1 given 19.99 U. Next for second isotope neon, atomic number 10, mass number 21, abundance given and also mass given m2, x2. First one x2 is equal, they have given only 0.27%. 0.27%, but the mass they have given 20.99 U. For third isotope neon with atomic number 10, mass number 22, x3 given and also m3 given. So x3 value 9.22%, 9.22%. And the mass is equal to 21.99%. 21.99. Now what they are asking? Find average atomic mass. Find average atomic mass. Find average atomic mass they are asking. Average atomic mass means how to find? Here 3 isotopes are given, means m1x1 plus m2x2 plus m3x3 should write. So average atomic mass m is equal to m1x1 plus m2x2 plus m3x3 whole divided by x1 plus x2 plus x3. So we'll get unified mass m. So for tomorrow class, so just substitute and solve this question, and the next class will continue and will solve the remaining problems. Correct. Okay, thank you.